see the location of the descending tract on the spinal cord, and then we're going to discuss where those tracts are located, what the function is, and we'll trace the descending tract one by one in detail. In fact, we'll only talk about the pyramidal tract in detail. So here we go. This is the spinal cord once again, and so when we talk about descending tract, the main tract which comes to everyone's mind is the pyramidal tract, or the corticospinal tract. That's a major descending tract we get. So we have a tract called as the pyramidal. The reason we call it pyramidal tract, the name given to the pyramidal tract, is because of the pyramids they are forming in the middle of longita. We'll see that in the brainstem. So we have elevation in the midline of the middle on the ventral aspect. We call them pyramids. The name given to them is pyramidal tract. But by the time pyramidal tract reaches the spinal cord, it is diffusated and everything is done. By the time it reaches the spinal cord, we have two parts of pyramidal tract we see here. One which is present in the lateral side of the spinal cord, and other part is seen in the anterior part of the spinal cord. And that's how they're named also. Let me try to label them together, this one and this one. This and this one. So that is placed anteriorly, so I name it as anterior. And this is placed laterally, so let's call it lateral. Anterior and lateral corticospinal tract. Anterior and lateral corticospinal tract. So these are the two components of the pyramidal tract. One is anterior corticospinal and one is lateral corticospinal. And as you can see, the nomenclature here is based on that where they are present in the spinal cord. Wherever they are coming from, wherever they are in the brainstem or wherever they are in the higher in the brainstem, in the internal capsule, that is not the point. The point is location of these tracts in the spinal cord. One is anteriorly placed over anterior, one is laterally placed over lateral. Corticospinal tract, from the cortex to the spinal cord, corticospinal. One of the difference of the lateral and anterior corticospinal tract is that, guys, anterior corticospinal tract are those fibers which are uncrossed, and lateral corticospinal fibers are the ones which are decussated or the crossed fiber. So this pyramidal tract will come to a certain level, and then some fiber will cross and some fiber will not cross. The one fiber which are not crossing and running on the same side of the spinal cord, then that tract is what anterior. But the one which decussate to the other side and then comes down into the spinal cord, those fibers are the lateral corticospinal tract. We will discuss that exactly how decussation takes place. Now, whether it is crossed or uncrossed, we are talking about the pyramidal tract, and the function of the pyramidal tract is obviously the skilled voluntary movements. Skilled voluntary movements. Or simply, it's a voluntary movement that is done by the corticospinal tract, both anterior and lateral. One difference is crossed and uncrossed, and there is another difference which we will discuss while talking about the tract. Then we have a tract which is present very close to the lateral corticospinal tract. Now, where this tract is very well developed in the lower animals, in human, they usually say this tract is basically this is the part assisting the corticospinal tract, coming from the red nucleus. Now, we do have red nucleus and we have a higher center also. In certain lower animals, this tract in us, which is coming from red nucleus, is the highest type of motor neuron system for them. So in us, it is coming from the red nucleus, and the name given to this obviously is rubrospinal. In rubrospinal tract. Now, if I tell you about the function of rubrospinal tract, it will be interesting if we discuss the rubrospinal tract along with another tract which is present very much in the anterior side here. The anterior side. And guys, this tract is coming from the vestibular nuclei, so obviously the name will be what? Vestibulospinal tract. Now, there is an interesting discussion. Vestibulospinal tract. We got a rubrospinal tract and we have a vestibulospinal tract. Now, the reason I'm talking about it together because their function is very contrasting. Rubrospinal tract function is to facilitate the flexors, like all the flexors. If I have to bend forward, I'm facilitating all my flexors. But it inhibits the extensors. So, like the extensors are inhibited when the rubrospinal tract is working. It is facilitating these flexors and inhibiting the extensors. Whereas vestibulospinal tract is exactly opposite. It facilitates extensors and inhibit flexors. And when you facilitate your extensors, you need to facilitate your extensors because you need to maintain a certain posture. Now, imagine if you're simply standing. If you're standing, guys, your posture, you're maintaining that posture is not merely because your legs are extended or your hip is extended. It's also because of your back muscles are having some sort of extensor tone. Imagine if there is no extensor tone in your back muscle, or if there is a vestibulospinal tract injury, then you will not be able to contract these, or involuntarily. I mean, these are the voluntary muscles, but without your any conscious effort, you're not able to control these muscles or maintain the tone of these muscles and cannot maintain the posture. Like, give an example. Vestibulospinal tract comes from vestibular nuclei, and we all know that vestibular nuclei is for balancing. So this tract coming from the brainstem all the way to the spinal cord is supplying the extensor muscle mainly, and keep on facilitating those extensors so that you can maintain a posture, whether it is standing, sitting, or whatever it is. So that particular posture is maintained with respect to the environment. And thankfully that is because of vestibulospinal tract. Comparison when we do. So we said rubrospinal tract. You remember it like this. Rubrospinal tract. It facilitate what? It facilitate flexors and inhibit extensors. You can write the full thing. It facilitate flexors and inhibit extensors. Facilitate flexors and inhibit extensors. Whereas vestibulospinal tract, on the other hand, it facilitate extensors and inhibit flexors. Facilitate extensors and inhibit flexors. That's why this vestibulospinal tract is a postural tract. It helps to maintain the posture. It's a postural tract. Rubrospinal tract facilitate flexors, inhibit extensor, and vestibulospinal tract is exactly opposite. It's facilitate extensor and inhibit flexor. Apart from that, another important tract that you should know, which is present in between the anterior corticospinal and vestibulospinal tract, guys, here somewhere in the anterior funiculus only. This tract is called as the tectospinal tract. I'll tell you more about this. It's called the tectospinal tract. So when you say the word tectospinal, look at the word tecto. Tecto word came from tectum, and tectum is a part of midbrain. Tectum is a part of midbrain. Now let me write the function first before we go any further. Tectospinal tract function is it basically coordinates the head and head and neck and eyeball movement based on any visual stimulus. Based on any visual stimulus. Let me take an example. Your head and neck movement and your ocular movement are generally they're done together, and this is something we usually don't pay attention to. I mean, if I'm turning my head to the side, my eyeball axis has also turned along with the head. Although if I wanted, I may not want to move my axis of eye, so I may want to fix it somewhere, and I want to move my head. Let's say if I'm watching a match and somebody calls my name from this side, or if I have to look at that side, something happened on that side, and I suddenly have to turn there. So I can turn my head to that side, but my eyeball can be fixed in front, or vice versa. I still keep on looking forward, keeping the face forward, but I can just turn my eye and can look on the other side. So that's a coordination between the head and neck and the ocular movement. Not necessarily every time you move your head, you have to move your eyeball also. That is actually up to you. Generally, unconsciously, what happens is, if I have to turn my head, so I will turn my head, my eyeball is also start looking at that side. If I turn my head to this side, my eyeball will turn to that side. Now, it doesn't happen like if you turn your head to one side, the eyeball will follow. So first your head will go, and then slowly eyeball will come. That doesn't happen, thankfully, because of this track. The tectospinal tract, it coordinates the movement of head and neck and eyeball. Coordinates the movement of head and neck and eyeball based on the visual stimulus. Based on the visual stimulus. I got a visual stimulus. If I got a visual stimulus, let's take another example. If I'm standing in the balcony and I'm watching a road and I can see there are some vehicles are passing by. So I'm looking at some car is going there from some Lamborghini or some nice car is going from there, and I started looking at it. Now I look at the car and I fix my eyeball to that car. I got a visual stimulus. I fix my eyeball to that car because I want to look at it. And now when the car is going, my head is moving along with it, and along my eyeball are also moving along with it. I'll keep on tracing the car till it is completely gone. So what happened here is, what is to be noticed here? My eyeball moved and my head and neck also moved together. It's not that I'm first waiting for the car to go till here and my eyeball will follow it, and then if my eyeball cannot work any further, then I started moving my head and neck. Then car will go further again, then again I move my eyeball, and then I move my head and neck. That doesn't happen. And that is because of we have this track, thankfully, that is tectospinal tract, which is for the coordinated movement of head, neck, and eyeball. Head, neck, and eyeball based on, that's important, based on what stimulus? Based on the visual stimulus. Based on the visual stimulus, because we will be discussing a track which will be having a similar sort of function, but based on the auditory stimulus. That is like MLF, medial longitudinal fasciculus. So that medial longitudinal fasciculus that we have in the brainstem, that will work in a different way. That will work based on the auditory stimulus. That you get an auditory stimulus from one side, and then you turn your head and neck and eyeball to that side. So that is an auditory stimulus. This is about the visual stimulus. Now there are other tracts also which are present at the cross-section level of the spinal cord, but we don't have to look into them. Like vestibulospinal, we have a reticulospinal, medial, lateral reticulospinal tracts are also there. So that we're just looking at the important one. Location of the tract is very important. I told you the location. If you know the location, then you can actually deal with the image-based questions. Because if you know the tract is present on the anterior side, so the question might be if there is an injury to the anterior most part of the spinal cord, then which tract will be gone? Like there is a question says syndrome called as Brown-Sequard syndrome, so all the tract of one side will be gone. There is a central canal syndrome, so the tracts which are close to the center, the tracts which are close to the centers will be gone, and the dorsal column tract will be spared. So the location is also very important. Just knowing the name and the function is not enough. You have to know the location also in this schematic diagram. Now there is some comparison that I want to do before we go to the pyramidal tract, and that comparison goes between the rubrospinal and tectospinal. Now you will say, what comparison is that? That is coming from red nucleus, it is coming from the midbrain, so how can you compare them? Their function are also not comparable. No, it's not about the function. It's about their morphology. It is about their topography, where they are present. Rubrospinal tract starts from the red nucleus, which is in the midbrain. Tectospinal tract is starting from the tectum, which is again a part of midbrain. So both these tracts, they start exactly from the same level of the midbrain. Both these tracts, they both decussate at the same level of the midbrain, and then they descend downward and reach the spinal cord. So that means if I get a transverse section of the midbrain, I will be looking at two decussation over there. So I should be able to identify that which one is for rubrospinal and which one is for tectospinal tract, because you may not see the fibers directly coming out of the red nucleus and decusating. So to understand this comparison, let me ask you to roughly draw this transverse section of the midbrain. That's how it goes. This is the transverse section of the midbrain. And let us say that section is taken at the level of the superior colliculus. That's important for us. This section is taken at the level of superior colliculus. How do we divide midbrain? Well, midbrain can be divided in three parts. This dorsal part of the midbrain, that's the one which I'm highlighting right now, where you can see colliculus, the superior colliculus, inferior colliculus. That dorsal aspect of the brainstem is called as the tectum. This portion of the midbrain is referred as the tectum. Then from the colliculus till the substantia nigra, this portion here, that part is called as the tegmentum. That is the tegmentum. And I don't have to tell you about this part, we already discussed it. This is called as the cerebral peduncle. I'm just writing CP over there, that is cerebral, not cerebellum, cerebral peduncle. And if you wonder why do we call it cerebral peduncle, it's a part of midbrain because the descending tracts from the cerebrum are present here only. Pyramidal tract or extrapyramidal tract, they are all located in this part here. So the name given to this is the cerebral peduncle, although it is a part of midbrain. We call it cerebral peduncle. So tectum, tegmentum, and cerebral peduncle. The dorsal part is tectum, middle part is tegmentum, and the ventralmost part here is the cerebral peduncle. And as we said, the section is taken from where? From the superior colliculus of the midbrain. Red nucleus is located in the tegmentum part. Guys, there is huge red nucleus present in the tegmentum part. Please notice that the fiber which are starting from superior colliculus, those fibers which will start from superior colliculus will come forward in the tegmentum and cross here. In the tegmentum, make sure the decussation is taking place in the tegmentum. And same thing here, the fibers which are coming from the red nucleus, they will also come in the tegmentum only, anyways it is in the tegmentum, and also decussates. Because fibers coming from superior colliculus are coming from which part of the midbrain? Tectum. So this is the tract called the tectospinal tract. The tectospinal tract, this is the one. And this coming from red nucleus, that is the rubrospinal tract. So in the midbrain, if you see a decussation more toward the posterior side of tegmentum, that is for the tectospinal tract, more toward the anterior side in the tegmentum, that is the rubrospinal tract. And that's why these decussations are also given name. This decussation here is called the dorsal tegmental decussation because it takes place at tegmentum, and this is ventral tegmental decussation. Please don't confuse guys. Dorsal tegmental decussation. The tract is tectospinal tract because it starts from the tectum, but decussation is in the tegmentum. So if I give it number 1 here, this one, and let me give it number 2. So 1 is the dorsal tegmental decussation. Dorsal tegmental decussation. And number two is ventral. It is present more anteriorly, so that's a ventral tegmental decussation. Dorsal tegmental decussation, as we said, it is for the tectospinal tract. It's a straight question. Tectospinal tract, and ventral tegmental decussation belongs to rubrospinal tract. They do ask a straight question on this, that which tract is for what? Which decussation belongs to what tract here? Dorsal for the tectospinal, and ventral tegmental decussation is for the rubrospinal tract. It could be an image-based question also. They can give you the section of the midbrain at the level of the superior colliculus, and they might show you the decussating fiber in the dorsal and the ventral part. You can understand that easily, because we know the tegmentum is more posteriorly placed, so obviously the decussation is also posteriorly placed. Okay, so this is about the two tracks which are decussating in. Now coming to the last major tract here, the pyramidal tract, how exactly it started, till what point it will go, and how it decussates to reach the spinal cord, to reach the effector muscles actually. So the final thing that we're discussing here is the pyramidal tract. Well, in case of pyramidal tract, this time we'll be looking at the motor cortex. Descending tract obviously will start with the motor cortex. Motor cortex is area number 4. 3, 1 and 2 was sensitive. Motor cortex is area number 4. The tract from the motor cortex will descend downward, will become a part of internal capsule and corona radiata. We will discuss that in the later part in the cerebrum only. I want to take your attention directly to the brainstem. Once these fibers they reach the brainstem, they're still on the same side. My right pyramidal tract starting from the right cerebral hemisphere, till the time it reaches the brainstem, it is still on the right side only. It is still on the right side. So guys, if let's say this here is the brainstem. So very schematically guys, let's say if this box here represents the brainstem, and we've got three parts here: midbrain, pons, and middle oblongata. If this here is midbrain, we've got pons, and that is middle oblongata. So we want to draw this midline passing through the brainstem and extend this downward all the way to the spinal cord. Okay, so that's the plot we'll be needing here. We've got a motor cortex, we've got three parts of the brainstem which are shown here, the midline, and that is the spinal cord. Obviously, we have some other details to be added in this, but our aim is to understand how the tract is reaching. We can always add those details later on. Now, the pyramidal tract starting from the motor cortex, it will run on the same side, like it is running close to the midline, but on the same side. Whether it is midbrain, pons, and middle oblongata, it is close to the midline only. And when these fiber reaches the middle oblongata, the lower part of middle oblongata, more precisely, so like these are 100% fiber here running on the same side. They're all total fibers are there. So till here, all 100% fiber are same side. But once they reach the lower part of middle oblongata, out of which 85 to 90% of fibers they will decussate. A huge number will decussate. 85 to 90%, imagine. And once they decussate in the middle oblongata, they again descend downward and reach the lateral part of the spinal cord. Look at this. Make sure you draw it on the lateral part of the spinal cord. And that's why this tract is called the lateral corticospinal tract, because ultimately it is coming to the lateral side of the spinal cord. That is 85 to 90% fibers. But remaining 10 to 15% fiber will keep running on the same side. Look at this. They'll keep running on the same side, and that means anteriorly or close to the midline only. And thereby they reach the anterior part of the spinal cord. That's why we call them anterior corticospinal tract. First point to be noted here, where the decussation is taking place. Pyramidal decussation is taking place in the lower medulla oblongata. This is pyramidal decussation. There is a pyramidal decussation, and that is taking place where? In the lower medulla oblongata. That's one question. They've asked this question more than once. What is the level for pyramidal decussation? It's just saying medulla oblongata is not enough, it's the lower part of medulla oblongata. What is the result? The result of this decussation is that 85%, let me stick to one number, 85% fibers are decussating to the other side, and they're giving rise to the lateral corticospinal tract. They're coming from the cortex, going to the spinal cord, so obviously corticospinal, lateral corticospinal tract, and the remaining 10 to 15%, let's go with 15% fiber running on the same side, that is the anterior corticospinal tract. That is anterior corticospinal tract. 85, 15. Reach the wide bed of the spinal cord. Still not out. We still have to supply the muscle outside. Now this is the interesting part, guys. 85 are decussating and 15 are not decussating. This thing is only true when we talk at the level of the brainstem. We say 85% fibers are decussating, 15 are not, because in actual, everything decussates. Even these 15% fiber, they will decussate, but the point is, they will decussate at the level of the spinal cord. See, you already know in the ventral horn, we have a lateral nuclei, let's say lateral nuclei, and we have a lower motor neuron coming out from here. And we have a medial nuclei from where again a lower motor neuron will come out. Just look at this, we are trying to explain this thing. Lower motor neuron from the lateral nucleus of the ventral horn, lower motor neuron from the medial nucleus of ventral horn. And why I'm marking this? Because you know that lower motor neuron coming from the lateral nucleus is going to supply what muscle? Limb muscles. Whereas the one which will be coming from the medial nucleus will be supplying the midline muscle or axial muscle. Right? That was it. And this will make sense to you. Obviously, for this lateral corticospinal tract, it's easy to come into the spinal cord and relay onto these lower motor neuron, which are toward the lateral side only. So these fibers will come in here and will relay at this point, and then obviously lower motor neuron will go out and supply limb muscle. Anterior corticospinal tract, what will it do? It will decussate at the level of spinal cord. Now, if it decussates at the level of spinal cord, obviously it is easy for them to reach where? The medial one. So they will decussate at this level here, and then they will relay to this medial group of nucleus, which is going to supply the midline or axial muscles. So this also tells me that lateral corticospinal tract and anterior corticospinal tract, the only difference is not the only difference they have. One is decussating and one is not decussating in medulla. The other difference is what muscle they are going to supply. So you can also note that the lateral corticospinal tract is going to supply the limb muscles, which again you remember with the term L. Lateral corticospinal tract, that is coming to the lateral nucleus of the ventral horn, supplying limb muscles. L. Anterior corticospinal tract, on the other hand, it decussates at the level of the spinal cord, coming to the opposite side, going to the medial nucleus of the ventral horn, and that's why supplying the midline muscle or axial musculature. Midline muscle or axial musculature. So that's the whole point, guys. I mean, this decussation, if we know about them, it will be easy for us to discuss them in the certain syndromes that we'll talk about. Like, if imagine if the injury is somewhere here in the pons or in midbrain, then if pyramidal tract is gone, obviously these fibers are gone, and even these 15% are also gone. Everything will be gone. So we have contralateral paralysis of limb muscles also and axial muscle also. But if the injury is only to the lateral corticospinal tract, then because anterior corticospinal tract is still working, so the axial muscles of that side will be spared, of the other side will be spared. But limb muscle still will be gone, and main feature will be seen in the limb muscles itself. So this is about the pyramidal tract, the main descending tract. So for all the important questions and syndromes, you should know about the dorsal column tract, talking about ascending, spinothalamic tract, spinocerebellar tract, very importantly, where they are decussating and where the lemniscus are. And in the descending tract, the main tract to remember here is the corticospinal tract and the level of decussation, obviously, which is the lower part of medulla oblongata. So guys, next in this the discussion in neuro, we're going to start with the brainstem. Well, after spinal cord, as we know the tracts already ascending and descending tract, but we also need to trace their pathway in the brainstem also. Like ascending tracts, as we already said, they're forming some lemniscus in the brainstem, medial lemniscus and spinal lemniscus we've already seen. And the brainstem we'll be talking about two more lemniscus, that is the trigeminal as well as the lateral lemniscus, which are related to the trigeminal nerve pathway and the auditory pathway respectively. But how we're going to approach the brainstem is, first we will look at the morphology, the external features. We will start with the ventral aspect of the brainstem and we see how cranial nerves are coming out. We've already discussed cranial nerve, but we need to know how exactly they exit the brainstem and from what point they are coming out. Then we also need to see from the front of the brainstem only that there's a fossa in between the two peduncles called as the interpeduncular fossa. So what are the boundaries of the interpeduncular fossa, what is its importance, and the content as well. And we also appreciate some perforating substances in the interpeduncular fossa and in relation to the interpeduncular fossa. So all these things need to be covered from the front of the brainstem. That will be the first thing. After that, we will turn the brainstem, and once you turn the brainstem, we expect to see cerebellum behind it. Behind the pons there is cerebellum. So we're going to remove the cerebellum because that we'll discuss separately. And you remove the cerebellum means you will be exposing the fourth ventricle because there's a fourth ventricle between pons and cerebellum. So looking at the dorsal aspect of brainstem, after removal of cerebellum will expose the diamond-shaped fourth ventricle. So we'll also be talking about the details of fourth ventricle. Then followed by we talk about certain pathways in the brainstem and finally about the syndromes. So this is a topic in which again whatever we discussed in the head and neck, the cranial nerve nuclei, the cranial nerve columns, the cranial nerves itself, and the tracts we discussed in spinal cord. So this topic is an amalgam of everything. So first we are looking at the ventral aspect of brainstem. Okay, let me draw it for you, and then I'm going to show you some pictures from the atlas also. If let's say this here is the pons. Here is the cerebral peduncle. The cerebral peduncle is a part of the midbrain only. If you remember, we said in the transverse section of the midbrain, you will be seeing a tectum, tegmentum, and the crus cerebri or cerebral peduncle, which is present anteriorly or ventrally. That's a ventral aspect. So these are the two cerebral peduncle. And inferior, let's say here we got the medulla oblongata. This is medulla oblongata, and let's presume this is the midbrain. So this roughly is the anterior aspect of the brainstem. That's how it's going to look like. There is a part of midbrain. This is a part of midbrain. And what part is that? That is cerebral peduncle. I'm writing CP here. That is cerebral peduncle. This is pons. Pons. The literal meaning of the word pons is bridge. It's basically bridge between the brainstem and the cerebellum. So if any tract has to go from brainstem to cerebellum or from cerebellum to brainstem, it may take a different peduncle, superior, middle, inferior peduncle, but ultimately they're all going from the level of the pons itself. And then finally we got this medulla oblongata. Between the two cerebral peduncle, this fossa here is called as interpeduncular fossa. This is what we got to discuss, that is interpeduncular fossa, but we'll be discussing it separately. The fossa, this is the, I'm writing interpeduncular fossa, IPF, interpeduncular fossa. And in the ventral part of the medulla oblongata, close to the midline, you will see these elevations which are called as pyramids. Clearly we call them pyramids because of the pyramidal tract. As we know, pyramidal tract will keep running on the same side, and in the lower medulla oblongata they decussate. So that's why you can see the pyramid present in the most of the part of the ventral aspect of medulla. And more lateral to the pyramid, you can see another very prominent elevation here called as olive. If we label them, just try to label them on side only. This is olive. Olive is because of what? Olive is, there's some nucleus which is present deep to it, and that is the inferior olivary nucleus. There's a huge nucleus present inside called as inferior olivary nucleus, and that is the one which is producing this bulge called as olive. And this, as we already said, this is pyramid. Pyramid is simply because of pyramidal tract. So ventral aspect of the midbrain showing you the cerebral peduncle, and the fossa in between is interpeduncular fossa. You can see the ventral aspect of pons here, and as I said, the pons acts like a bridge. So all the peduncles, whether it is midbrain peduncle or medullary peduncle, they all go toward the pons first, and then they enter into cerebellum. That's why the word bridge is given to it. And then we have medulla. From the ventral aspect of medulla, the two major elevations that you'll appreciate. One is olive. Let me just highlight them so that we can see how cranial nerves are coming out. This is olive, and more close to the midline, that's pyramid. These are pyramids. You will keep calling them pyramids till the decussation takes place because all 100% fibers are present in the ventral part. No decussation, that means 100% fibers are here only. In the lower medulla oblongata, we know that 85 to 90% fibers will decussate. So only 10% fibers will be left in the anterior part. So the pyramid will be gone. I mean, they will vanish. So you can only see pyramid in the lower medulla oblongata. The first thing, how cranial nerves they exit, how cranial nerves are coming out of the brainstem. Third nerve, we already discussed that in the cranial nerves. Third nerve is the content of interpeduncular fossa, and that's why you will see third nerve emerging like this from the interpeduncular fossa and winding around the cerebral peduncle. That is third nerve. Fourth is the only cranial nerve coming from dorsal aspect of brainstem. So that's the only nerve you see coming from the dorsal aspect of brainstem, and that is also winding around the cerebral peduncle. So that again could be a question: what are the two nerves which winds around the cerebral peduncle? The third nerve from the interpeduncular fossa, and fourth nerve is the one coming from the dorsal aspect of brainstem. Yes, pons is having many nuclei inside. There's so many nuclei we have inside the pons: facial nucleus and motor trigeminal nucleus and salivatory, inferior salivatory. But when you look at the nerve coming out, now it's not necessary that exactly where the nucleus is present, the nerve also need to come out from there. Because one nerve can have multiple nuclei. That's why don't think that facial motor nucleus is in pons, so the facial nerve should come out from here only. No, not necessary. So when you see the ventral aspect of pons, there is only one nerve that you see coming out from here, and that too very much toward the lateral side from the pontocerebellar angle region, and that is the thickest cranial nerve, the trigeminal. The fifth nerve is the only nerve emerging from the ventral aspect of the pons. Despite having many nuclei inside, only one nerve comes out from the ventral aspect of pons, and that too very much toward the lateral side, that is the fifth nerve. Pontomedullary junction. Now that's an important point from where multiple nerves are coming out. Very close to midline, you will see the sixth nerve, then got seventh nerve and eighth nerve. We're just looking at the nerve of one side only. This is sixth nerve. Here's the seventh, and there we got eight. 6, 7, and 8. So what do you see for the sixth, seventh, and eighth nerve? I can say they're all coming out from what junction? Pontomedullary junction. Now yes, we can say 6th, 7th, and 8th nerve are coming out from pontomedullary junction, but this question can be more precise that where exactly from pontomedullary junction. If you see 6th nerve is emerging from the ponto-pyramidal junction, if you talk about which part of medulla, pyramidal part, and 7th nerve is coming from ponto-olivary junction. So make sure you also note that the 6th nerve and 7th nerve, the 6th nerve emerges from ponto-pyramidal junction, and 7th nerve from ponto-olivary. Ponto-olivary junction. So that is 6th, 7th, and 8th nerve from the pontomedullary junction, more precisely 6th and 7th from ponto-pyramidal and ponto-olivary respectively. Lateral to olive, you can see the 9th, 10th, and 11th nerve. 9th nerve, this 10th, and 11th nerve, they're all emerging just lateral to olive. If you remember, the common thing between these three nerves was they were all coming from nucleus ambiguus, and nucleus ambiguus was present in the middle oblongata. So 9th, 10th, 11th nerve, they emerge from the ventral aspect of the medulla, but remember, we're lateral to olive. These nerves are present lateral to olive. And finally, the only nerve that you see emerging between the olive and pyramid is the 12th nerve. That's the only nerve which emerges between pyramid and olive. See, these information are so important that right now it looks like we just have to know that where the nerve is coming out from, but when you take a transverse section of the medulla or any part of the brainstem for that matter, if you have an idea about how cranial nerve is coming out, so that will also help you identify in the transverse section also. Like when you take a transverse section of medulla oblongata, it's very easy to identify the olive and pyramid. You can very easily identify this close to the midline is pyramid and more laterally we have olive. And then if in the transverse section they've shown some fiber coming out from there, you can make out, okay, if a nerve is present lateral to olive in the transverse section, it has to be either 9th, 10th or 11th nerve, and the only nerve which will be running between pyramid and olive close to the midline is 12th nerve or hypoglossal nerve. If you notice one more thing from this arrangement here, alar plate and the basal plate we talked about, one is a sensory plate, one is a motor plate. Well, this may not indicate everything in that sequence, but most of the motor nerves, not all, most of the motor nerves are seen relatively close to midline only. If you see third nerve, it's close to the midline. 6th nerve, 7th nerve, closer to the midline only. 12th nerve, closer to the midline. And that is why the third nerve and 6th nerve and 7th nerve and hypoglossal nerve, they will be involved in the syndromes of the brainstem which are affecting close to the midline only, like Weber syndrome or medial medullary syndrome. We will discuss that. So just can have an idea about from the morphology only that what nerve are present. So third and fourth, finding out the peduncle. Fifth is the only nerve from the ventral aspect of pons. 6th, 7th, 8th from pontomedullary junction. 9th and 11th lateral to olive, and 12th nerve is between pyramid and olive. Let me take your attention from this part to the interpeduncular fossa now. Let's focus only to the cranial part of this ventral aspect of brainstem. But before that, I can show you one picture in which you can appreciate how the nerves are coming out. Now that's an atlas image, and as you can see the brainstem over there, the one, look at those lines over there, that represents the cerebral peduncle. That's the peduncle part, so it's midbrain. This whole thing is pons, and here we got medulla oblongata. Can you appreciate in the medulla oblongata, these are the pyramids, and lateral to pyramid, those elevations are the olive. So the nerve that we already discussed in there, this is the third nerve. Now look at this nerve, that is the fourth nerve, and the two nerves that you see on the sides of the peduncle. Then we got this huge fifth nerve coming from the ventral aspect of pons. Look at the entire pons, only one nerve is coming out. Although you see two roots of the fifth nerve. Fifth nerve is predominantly sensory nerve. So we have a thicker sensory part, and then a thinner motor part. That's a motor part only, which will contribute to mandibular nerve. But overall, it's a trigeminal nerve only coming out from the ventral aspect of pons. Pontomedullary junction, look at the nerves. The sixth nerve. Then we have again, look at these two. There is seventh nerve, and there is eighth nerve. Now why are you seeing again 2 and 7? Because that's a mixed nerve again. Facial nerve is predominantly motor, and we have a sensory function also. So thicker part there will be the motor part, and thinner part will be the sensory part. But that is facial nerve. 6th, 7th, and 8th nerve. I repeat again what I said, for the trigeminal nerve, it is a predominantly sensory nerve, so thicker portion will be the sensory root and thinner one is motor. But facial nerve is predominantly a motor nerve, so thicker part is motor and thinner one is sensory. You can see 9th, 10th, and 11th nerve coming out from the lateral to olive. And you can appreciate both the part of 11th nerve. You can see cranial accessories coming out from the brainstem, and look at spinal accessories ascending upward all the way and then coming out along with the cranial accessory only. Remember we said spinal accessory will go through foramen magnum, reach the cranial cavity, and then again comes out from jugular foramen. So you can see both cranial as well as spinal accessory. And this nerve here, which is between pyramid and olive, is the 12th nerve or hypoglossal. That is hypoglossal. Now please don't get confused with this nerve over there. But that's not a spinal nerve. That is not a cranial nerve. That is a spinal nerve. That's the first cervical nerve. The same sulcus which is present between the pyramid and olive. If you extend that sulcus downward, it is going to the spinal cord also. So that is the first cervical nerve we're looking at, the C1 nerve. So exactly the same sulcus where we have hypoglossal nerve in the brainstem. If you trace that sulcus downward to the spinal cord, then you start looking at the motor branches of the spinal nerve, the C1, C2, C3, C4, so on. So as I said, right now let's focus on to this fossa, what is called as interpeduncular fossa. This fossa here is the interpeduncular fossa which we got to discuss. When we complete this diagram, we'll see that anteriorly in the interpeduncular fossa we have optic chiasma, and on the sides we have optic tract also, and that completes the boundary of interpeduncular fossa. So let me take you back. So we're going to draw only the cranial part of the brainstem now. I request you to start slightly below because we have to ascend upward in this diagram. So if this is the, once again, pons, and here are the peduncles. And let's complete this fossa here, the interpeduncular fossa, by drawing the Optic path. So this is the optic tract and chiasm. That is the foci between the interpeduncular fossa. So if I have to mark the boundaries of this fossa, it starts with this optic chiasm which is present in the midline ventral, that is optic chiasm. Then we got this tract. And this is peduncle, the cerebral peduncle. I hope you know the other name of cerebral peduncle. It is also called as the crus cerebri. Crus cerebri, cerebral peduncle or crus cerebri. Peduncle or this crus means white matter only. It's a white matter tuft that you see, and we call it cerebral peduncle or crus cerebri. Why the word cerebral peduncle? We discussed that earlier also, because the descending tracts from cerebrum are situated inside only. Pyramidal tract, extrapyramidal tract, they are all present in this peduncle part, and then they go to the pons and medulla. So guys, obviously the foci between is interpeduncular fossa. So boundaries are quite visible from here, the optic chiasma, tract and the peduncle. What are contents inside? The contents of interpeduncular fossa includes, we got infundibulum, the stalk of pituitary, infundibulum, and this infundibulum extending from the elevation called as tuber cinereum. So let's say number one over there is a cut section of infundibulum coming from this tuber cinereum. This elevation is called as tuber cinereum. Then we have this component of limbic system present here called as mammillary bodies. Let me give it number 2. Number 3, we already discussed that is the third nerve. We said oculomotor nerve is a content of interpeduncular fossa, so let's give it number 3. And number 4 is a perforation that you will see in the posterior part where some blood vessels will be seen going inside. We call it posterior perforating substance. That is number 4. That is number 4. So optic chiasma, optic tract and cerebral peduncle, these are boundaries of interpeduncular fossa. These are the boundaries of interpeduncular fossa. Whereas contents, I've marked the contents with numbers, let's write about them. Contents are number 1. Number 1 is infundibulum, that is the stalk of pituitary, infundibulum and tuber cinereum. Tuber cinereum. Number 2 is mammillary bodies. Mammillary bodies. Mammillary bodies are the one where the fornix will end. Something we'll discuss later on. The fornix, that white matter bundle which starts from hippocampus, will end in the mammillary bodies. Number 3 is for the third nerve, that is oculomotor nerve. And number 4, which you should know more about, that is posterior perforating substance. That is called as a posterior perforating substance. Now when you say something as a posterior perforating substance, it's an indication that there must be some anterior perforating substance also. If this is posterior perforating, now where is anterior perforating? Anterior perforating substance is not present inside the interpeduncular fossa, it is outside. For that I need to add something more to this diagram. Now guys, let's presume if this here is the olfactory bulb and this is olfactory tract, and what you will see, the olfactory tract will divide in a medial stria and a lateral stria like this. This is the olfactory bulb, we are just looking at one side only. This is olfactory bulb. This is obviously olfactory tract, and then you can see the two divisions of the olfactory tract, the medial and the lateral division or stria you can say. And between these medial and lateral stria or lateral to optic chiasma, this is the point where we have the anterior perforating substance. Here we have the anterior perforating substance. I'm writing APS, anterior perforating substance. So location wise it is more anterior, so anterior perforating, this is posterior perforating. But the question is, what exactly are perforating substance? Well, it is an area or it's a gray matter of the brain stem which is perforated by certain arteries. See, the blood vessels which are running on the surface of the brain or brain stem, they need to supply the core also. But how do they reach the core? Once they pierce the parenchyma, the gray matter and the parenchyma of the brain stem and cerebrum. So you will see some branches of a major artery here piercing this region, so we call it posterior perforating, and some branches are perforating that, so anterior perforating. Now to tell you what exactly branches are those, let me show you one picture. Now, this time I'm showing you a real-time section of the ventral aspect of the brainstem along with the blood vessels on it. Now you're looking at this picture where you can see interpeduncular fossa clearly, that whole thing is the interpeduncular fossa. You can appreciate the boundary, we got optic chiasma there. This is optic tract. There will be cerebral peduncle which is hidden by these blood vessels and all. So these are the boundaries. Content-wise, look at where I'm pointing at. This is infundibulum and tuber cinereum. Look at this. This is infundibulum and tuber cinereum. You can see those two mammillary bodies. Third nerve. Can you see the third nerve over there? That's the third nerve coming out here. And when we discuss the third and the fourth nerve in the cranial nerves, we said the nerves are coming out between the two arteries. I want you to appreciate the two arteries also. Guess what artery is this? The artery running in front of the brainstem, that is basilar artery, correct? That is a basilar artery. And we all know that basilar artery divides into a terminal branch called as posterior cerebral artery. Now this here is posterior cerebral, and just proximal to posterior cerebral, this is the superior cerebellar artery. Both are branches of basilar. Terminal branch of basilar is posterior cerebral, and then we have superior cerebellar artery, and between these two arteries, can you see third nerve as well as thin fourth nerve coming out? Look at this thin nerve here, fourth nerve. Third and the fourth nerve, both nerve emerges between the posterior cerebral and superior cerebellar artery. So till now we can see the optic infundibulum, we can see here mammillary body and third nerve. Now this you can see is the area called as posterior perforating substance. And I hope you can make out from this picture that why we call it posterior perforating, because the branches of PCA, look at these branches going from here. The branches of posterior cerebral artery are piercing this gray matter area to reach inside and supply the core structures there. So gray matter area in the interpeduncular fossa perforated by the branches of PCA is posterior perforating substance. I will write this for you, but look here. What about anterior perforating? Now this is anterior perforating, look at that, that is anterior perforating. Now what blood vessel is, you can see the major internal carotid artery is present over. And we know that internal carotid artery gives off, a direct branch of internal carotid artery is anterior cerebral as well as middle cerebral, which is going into the sylvian sulcus. You can see it here also, this is internal carotid, it gives off anterior cerebral going forward and middle cerebral is going toward the sylvian sulcus. So that means both anterior cerebral and middle cerebral are present in this region, And that's why both ACA as well as MCA will give the perforating branches entering through this part, and that's what anterior perforating substance is. So anterior perforating substance is a gray matter area perforated by the branches of both ACA and MCA, both anterior cerebral and middle cerebral, whereas posterior perforating substance is the gray matter area perforated by the branches of only PCA. Let me just write that for you as well. So what we said, anterior perforating substance, this here is the gray matter area, perforated by the branches of PCA, posterior cerebral artery, perforated by the branches of PCA. Whereas on the other hand, this anterior perforating substance is the gray matter area which is perforated by the branches of anterior cerebral as well as middle cerebral, both anterior as well as middle cerebral artery. They do ask question on this. So posterior perforating substance, only posterior is there, and anterior we have both anterior as well as middle cerebral artery branches. Now there's another question here which is asked twice, and that is about the relations of anterior perforating substance. Anterior perforating substance relation. Now two relations are quite clear from this schematic picture only. That medial relation is optic chiasma and posterior relation is optic tract. Now what is going to be the lateral relation? What is there outside? Now strias are there, fine, but relation, what is there outside? Medial is optic chiasma and posterior is optic tract. Again, this picture will help you understand that those relations. If I take you back here, now look at the anterior perforating substance. Medially we have this chiasma, that is optic chiasma, this is the one, and posterior we got optic tract. But laterally, now can you see that sulcus in which middle cerebral artery is going? That sulcus over there is the limen insulae. Limen insulae. That is the point from where the lateral sulcus will begin. We have a lateral sulcus on the outer side, but lateral sulcus of the brain starts from the inferior aspect, then it goes like this, and then on the outer aspect it comes and divides into three divisions. We have divides into three branches. We have an ascending branch and posterior branch and all. You will see that from the superior lateral surface. So overall, this point over there where you see the middle cerebral artery is entering over there, this region is called as the limen insulae. And more behind that, or posterior to that, we have a part of the cerebrum called as uncus. If you remember, uncus was forming the lateral relation of cavernous sinus, the same uncus. So if the question is precisely about the lateral relation, your best answer is limen insulae, and more posterior laterally we have uncus present. So if I write the relations of anterior perforating substance, so first medial relation was what? That was optic chiasma. Posterior relation is optic tract, and then comes the important one, that is lateral relation. Your best answer here is going to be limen insulae. If limen insulae is not in the option, you can go with uncus also, but uncus should be your second best choice. Limen insulae, uncus. Uncus is more posterior laterally present. So this is about the ventral aspect of the brainstem. So what all we discussed on the ventral aspect, we saw how cranial nerves are coming on. That's one important thing because they do ask a lot of image-based question in which you need to identify the nerve. So they will simply say, okay, injury to which of the following nerve will lead to the divergent squint. So if first we need to know divergent squint is by which nerve, then we need to identify that nerve on the brainstem also. So the pictorial representation of all these nerves are very important. We talked about interpeduncular foresights boundary, its content, and also about the perforating substance with a special emphasis on the relations of anterior perforating substance. Now it's time to turn the brainstem, guys. Let us turn the brainstem, and this time, as I said, from posterior aspect we have to remove the cerebellum. And once you remove cerebellum, we said the fourth ventricle will be exposed. What I'm going to do is I'm going to show you a picture first, and then we'll draw it. It will be easy for us. So if I take you to the dorsal aspect of brainstem, this is going to look something. Let's look at this low magnification first. Now this part here is the midbrain. Don't worry about that part. That is the thalamus. You can see a portion of thalamus can be seen extending backward here. So this is the midbrain part. And how can I say midbrain? I can see four colliculus over there. Two superior colliculus and two inferior colliculus. Please don't worry about this. This is pineal gland, which is not a part of discussion as of now. That's a pineal gland, so let's exclude it from here. Apart from that, you can see the two superior colliculus. Let me write over it. We have superior colliculus and these are inferior colliculus. And superior and the inferior colliculus together are called as corpora. We call them corpora quadrigemina. Four gem-like structure, corpora quadrigemina. And if you remember, there was a cistern present behind this and above the cerebellum. We call it superior cistern or quadrigeminal cistern. So that is basically facing these corpora quadrigemina only. And what is also to be understood from here, that cerebellum, even if you remove the cerebellum, the midbrain is not going to get affected because behind midbrain there is no cerebellum. Cerebellum is present behind the pons and upper medulla. So remove the cerebellum from the brainstem, you're literally distorting the dorsal aspect or posterior aspect of pons and upper medulla oblongata, but not the midbrain. So if the cerebellum is there or not there, this portion is still intact. Just below these four colliculus, can you see those nerves coming out? Well, I hope you can easily identify that is the only cranial nerve coming from the dorsal aspect of brainstem. That is fourth nerve. And I told you in the cranial nerve discussion that the decussation of fourth nerve, it takes place within the midbrain and then they come out. That means this fourth nerve is coming out from the nucleus present on the other side. So the decussation has already taken place within the midbrain only, and then the nerves are emerging out. In some text or some pictures on the Google, they've shown that decussation is outside the brainstem. That is not true. It is inside the brainstem. And then you're looking at this fourth ventricle over there. That is the floor of fourth ventricle. But before we talk about fourth ventricle, you first need to look at the boundaries there. What are the structures forming the boundary of fourth ventricle? Well, how will you remove? When I said remove the cerebellum means how you need to cut the cerebellum. You have to cut the peduncles. The only way cerebellum is connected to brainstem is through cerebellar peduncles, superior, middle, inferior. Once you cut the cerebellar peduncle, then obviously cerebellum can be detached. If you look carefully, look at that white matter bundle where I'm pointing it right now. This white matter bundle is coming from above. That is from midbrain. So this has to be the superior cerebellar peduncle. The one which is coming from below here, look at this one. They've shown the different shade also. That is inferior cerebellar peduncle. And the one which is more outside, shown in the lighter shade, that is the middle cerebellar peduncle. Cerebellar is standard. This is superior cerebellar peduncle. This is inferior, and this one is a middle cerebellar peduncle. And what is very, very interesting to note here, that superior and the inferior cerebellar peduncle, they converge in such a way that they both fuse, and that leaves the middle cerebellar peduncle outside. So when you talk about the boundary of the fourth ventricle, we are not going to count the middle peduncle. When you're looking at the boundary of fourth ventricle, we are not going to count the middle peduncle because that is outside now. So we've got a superior peduncle coming from above, inferior cerebellar peduncle from below, fusing. And is there anything else forming the boundary? Yes, there is. Guys, if you look at this portion of the medulla oblongata, So it is a continuation from the spinal cord. Now I want you to think about it. If you think about the spinal cord, what is there at the dorsal aspect of spinal cord? At the dorsal aspect of spinal cord, we have a dorsal column tract having fasciculus gracilis and fasciculus cuneatus. So that means this, you look at my finger here, this is fasciculus gracilis here, and this will be the fasciculus cuneatus. And we know that the nuclei for the fasciculus gracilis and cuneatus are in the middle of oblongata and they're present in these elevations only. And that's why they're elevated, because we have a nuclei present deep to them. So we have a nucleus gracilis and nucleus cuneatus present inside. And that's why these tubercles are called as a gracile tubercle and cuneate tubercle. That is the point where the first order neuron of dorsal column tract are ending here. That is a gracile tubercle and cuneate tubercle. So overall, the boundaries of the fourth ventricle when I talk about, so it has to be the inferior cerebellar peduncle, superior cerebellar peduncle and inferior cerebellar peduncle. Middle stays out, so let's not count it. And the lower part, we also have a contribution from the gracile and cuneate tubercle. I'm going to redraw everything in a schematic way. First I want you to understand it here. Then inside the fourth ventricle, in the floor of fourth ventricle, what you'll see. Now in the floor of fourth ventricle, this sulcus here is called as the sulcus limitans. The same sulcus limitans which we said earlier, dividing the neural tube in two parts. So that sulcus over there is called a sulcus limitans. So when the neural tube opens, we said the alar plate is the one which goes toward the lateral side and basal plate is toward the medial side. That means the one toward the lateral side, one which is lateral to the sulcus limitans. This is going to be the alar plate. And I hope you remember the alar plate was sensory. So the nuclei which will be present deep to this alar plate will be some sensory nuclei. Whatever it will be sensory nuclei. But medial to the sulcus limitans, all these elevations that you see are because of those nuclei which are motor in nature. We have a facial colliculus, we have a the triangle where we have a hypoglossal nerve and vagus nerve nucleus situated. So the motor nerves are the one which are or nucleus situated medial to the sulcus limitans. We have some white matter bundle also to be seen. I'll come to that. Let's first discuss till this part. So looking at the dorsal aspect. Dorsal aspect of brainstem, and what else we'll achieve by looking at the dorsal aspect of brainstem, we also will be looking at the floor of fourth ventricle. We'll be looking at the floor of the fourth ventricle, which because of its shape is also called as a rhomboid fossa. Because of its shape is also called as a rhomboid fossa. So here we go. These are the two colliculus, the two superior colliculus and the two inferior colliculus. So starting from the midbrain part, we got superior colliculus and inferior colliculus. And as we already mentioned, these four colliculus together are called as the corpora quadrigemina. Corpora quadrigemina. This here is the floor. So we got a superior cerebellar peduncle converging downward. This is inferior cerebellar peduncle. Then we got this is inferior going above, and then meeting with the middle cerebellar peduncle, which is more laterally placed. Superior, inferior, and that is middle cerebellar peduncle. Let me label this. This is a superior cerebellar peduncle. Let me just draw this arrow that is converging toward the pons that is coming downward. Here we have ICP, that is inferior cerebellar peduncle, which is going upward, and they're all fusing along with middle cerebellar peduncle and entering into the cerebellum, which is removed from this picture. And then we also said, close to the midline, you will see the gracile tubercle and cuneate tubercle will also be contributing to the boundary. The gracile and cuneate tubercle. The tubercle which are because of the nucleus present deep to them. Nucleus gracilis and nucleus cuneatus is present deep to them, so that's why we call them gracile and cuneate tubercles. So that's the boundary thing. As I said, in the floor of fourth ventricle, we will see the sulcus limitans. Now, let's say this is sulcus limitans. First, it converges, just draw it in this way only, so that I can show the nuclei. So this is sulcus limitans, the one which was dividing the neural tube into the dorsal part called as the alar plate and the ventral part which was basal plate. And therefore, everything that you see medial to sulcus limitans is made up of basal plate. We got to have motor nuclei in this region here. We will be having motor nuclei present deep to this part, and sensory nuclei will be present lateral to the sulcus limitans here. The most important elevation, and on which one question is asked multiple times, that is the elevation called as the facial colliculus. Well, in the region of pons only, we use this term earlier also. This is the facial colliculus. Facial colliculus. We'll talk about facial colliculus a little more in a while. Facial colliculus. Below facial colliculus, this triangle here, this triangle, I can mark this portion. We have a nucleus present deep to this. There is a hypoglossal nucleus present deep to, so we call it hypoglossal triangle. We got a hypoglossal nucleus present here, so we call it hypoglossal triangle or trigone, some author says. Triangle or trigone. And further below, we have a dorsal nucleus of vagus present here. That's why it is called as the vagal triangle. So look at these three elevations. I'm trying to use the same color, that is facial colliculus, the hypoglossal triangle, and vagal triangle. And we said what is common between them? They are all developing in the basal plate. So you got to have a motor nuclei present deep to them. The one mistake which people do in this part is in the facial colliculus. The name is facial colliculus because facial nerve is winding around sixth nucleus. So if I have to ask this question, that what nucleus is present deep to this elevation? What is the nucleus deep to the elevation? So it's not the facial nucleus, it is the sixth nucleus. Facial nerve is winding around it, and that's why the name is facial colliculus. So facial colliculus is having sixth nucleus deep to it and not seventh, sixth nucleus. For the rest of the two, it is fine. We have a hypoglossal nucleus there. I'm writing nucleus, and the vagal nucleus is there. What about on the lateral side? On the lateral side, lateral to sulcus limitans, that elevation is called as a vestibular triangle. That is a vestibular triangle. And the nucleus present deep to the vestibular triangle is obviously the eighth nerve nucleus. So eighth nucleus simply, let me say. Vestibular nucleus, the eighth nucleus. So guys, first and the most important thing to note, if the question says what are the nuclei present in the floor of fourth ventricle or projected in the floor of fourth ventricle, don't write 7. It is 6, 8, 10 and 12. If I go in a sequence, 6, 8, 10 and 12. So make sure to write it nucleus or nuclei, not saying no, nuclei present in the floor of fourth ventricle. Nuclei present in the floor of fourth ventricle involves 6, 8, 10 and 12. 6, 8, 10 and 12. 6, 8, 10 and 12. But there's something very interesting about the facial colliculus. We said facial nerve is winding around this 6 nucleus and comes out. Now what is the need for that? Why facial nerve has to wind around any nucleus to come out when the facial nerve simply has to come out from the ventral aspect of brainstem? What I'm trying to say, if I tell you a little more about this facial colliculus, guys, if there's a section of the pons, we'll be discussing about this section in a while. It's a transfer section. It's a transfer section of the pons. And here we have 6th nucleus. And somewhere inside we've got a 7th nucleus. So what I'm saying is that 7th nerve will wind around like this and then it emerges out. That's how the 7th nerve is coming out by winding around, and we also call it the internal genu of the facial nerve. You know that. There is an internal genu of the facial nerve. When the bent is called as internal genu, bent is called as internal genu, and this elevation which is produced on the surface here, this one, this is called as the facial colliculus. Because of the facial nerve, so we call it facial colliculus. First, let's understand that what is the need for all this. Why facial nerve has to wind around the 6th nucleus and comes out when the facial nerve can simply come out like this only? Well, if you think about all the cranial nerve nuclei, once again that topic becomes very important. If you think of all cranial nerve nuclei, now the main motor nucleus of face is facial nucleus. We know that facial nucleus is applying majority of the muscles, or in fact all the muscles of facial expression. And the main sensory nucleus of the face is trigeminal nuclei. Now, can you think of that where those nuclei were located? If you think of facial nucleus, which was present in the second column, SVE, pharyngeal arch column, the very second column was for the facial nucleus, and the second last column was for the trigeminal nuclei, the GSA, general somatic afferent column. SVE column and general somatic afferent column are far apart from each other. And imagine if your facial sensory and motor nucleus are situated very far from each other in the brainstem, then the speed of the reflexes will be very, very slow. You need to have quick reflexes. And how can you have quick reflexes if the nuclei are situated close to it? Now, out of the trigeminal nuclei and facial nuclei, you can imagine it like this: the trigeminal nucleus is huge. It's a big trigeminal nucleus we have, but facial nucleus is in the pons, it is a smaller nucleus. So developmentally what happens is facial nucleus actually migrates towards the trigeminal nucleus, and during this migration, it actually winds around the abducent nucleus. That's why the internal genu is formed. This phenomena, where a sensory nucleus and the motor nucleus, they come close to each other so that the reflexes becomes a little fast, is called as neurobiotaxis. That is called as neurobiotaxis. So I can say this internal genu is a resultant of a phenomena called as a neurobiotaxis. Neurobiotaxis. What is neurobiotaxis in this case here? What is neurobiotaxis in this case? That motor facial nucleus migrates towards which one? Towards sensory trigeminal nuclei. Motor facial nucleus migrates towards the sensory trigeminal nuclei for faster reflexes. That's what you call as a neurobiotaxis. Neurobiotaxis. Now, how examiner tried to trick us in this question is, I've seen this question asked in AIMS twice in a row, and both the time the question was entirely different though. They gave us a picture of the floor of fourth ventricle, both the time same picture only, and the arrow was pointed at facial colliculus. Now let me just bring it back here. Now this is facial colliculus we have here. Let's say if I put an arrow on the facial colliculus, and the first time the question was pretty simple. The question was that what is the nucleus present deep to the following elevation. So although we call it facial colliculus, but the nucleus present deep to it is the 6th nucleus, abducent nucleus, and most of the people who read about the fourth ventricle, they got it right, no problem. Very next year, what they did, they gave the same picture of the floor of fourth ventricle. They again put the arrow on the facial colliculus, but this time the language of question was completely different. The question this time was injury to the structure producing following elevation. Look at this one. And again, facial colliculus. Injury to the structure producing facial colliculus or producing this elevation will lead to the paralysis of which muscle? Now, we said what nucleus is present deep to it is abducent nucleus. So if you think about abducent nucleus, you will mark the answer as lateral rectus. But that's not the thing. We know that abducent nucleus is surrounded by the facial nerve. What facial nerve is winding around this abducent nucleus. So every time you have injury to the facial colliculus, the first thing to go is facial nerve only. Facial nerve is the one which is winding around it. So when you say injury to facial colliculus, the first structure to be injured probably here is the facial nerve. Lower motor neuron of facial nerve will be there, and we know that if there is a lower motor neuron lesion of facial nerve, it leads to ipsilateral facial paralysis. So let me write this point as well here. That injury to, if the question says injury to structure producing facial colliculus. Injury to the structure producing facial colliculus means lower motor neuron lesion of facial nerve. Lower motor neuron lesion of facial nerve, and that we, as you already know, will lead to the ipsilateral facial paralysis. Don't go with lateral rectus as an answer. They purposefully gave lateral rectus in the option so that people mark it. If the question would have said injury to the nucleus present deep to the following elevation, then you will say okay, abducent nucleus will go because they have asked the question based on the nucleus. But if the question simply says injury to the structure producing facial colliculus, the facial colliculus is mainly because of facial nerve which winds around the abducent nucleus. So answer has to be the facial nerve injury in that case. If I take you back to this picture, there are few more things to look here. Like the nerve that we said coming from the dorsal aspect of brainstem, and that was the fourth nerve. The trochlear nerve will be seen emerging from the dorsal aspect of brainstem, just below inferior colliculus. You know, fourth nerve nucleus was at the level of inferior colliculus only. So the nerve is seen coming out below the inferior colliculus after decussation and winds around the peduncle. It is also to be noted that this inferior angle when you look at this very much inferior angle of the fourth ventricle, this is the site where the blood-brain barrier is not present. Where the blood-brain barrier is not present, and what we said, the area devoid of blood-brain barrier, which are called as circumventricular organ, and one of the circumventricular organ is here only. That is what? Area postrema. The vomiting center, the area postrema. Area postrema, you can note that it is also called the vomiting center of the brain. Area postrema is the vomiting center of the brain. One more term if you want to add here, if you look at the inferior angle, guys, if you look at the entire inferior angle of the fourth ventricle, the shape of the inferior angle of fourth ventricle looks like a nib of an ink pen. Can you see it looks like a nib of an ink pen in this lower part here? And that's why the inferior angle of fourth ventricle is also regarded as calamus scriptorius. Calamus is for the pen, calamus word is for the pen, scriptorius, the one which is used to write the script. So inferior angle of the fourth ventricle is also known as the calamus. Calamus is for the pen, scriptorius. Calamus scriptorius. So this is about the dorsal aspect of the brainstem, where we saw some part of the midbrain as superior and the inferior colliculus and the fourth nerve coming out. We saw an important part of the medulla also, the gracile and the cuneate tubercle, and the main thing that we saw is the floor of fourth ventricle. Now if I just talk about fourth ventricle, just to summarize it in one place, if you just write down the points regarding the fourth ventricle. So first of all, starting with the boundaries, what structures are forming the boundaries of the fourth ventricle? It was a superior cerebellar peduncle, it was inferior cerebellar peduncle, it was gracile tubercle, and also cuneate tubercle. Gracile and cuneate tubercle. Those are the boundaries. Floor, well, floor we already discussed in detail, that is rhomboid fossa only. Whatever we just discussed is all about the floor only. So rhomboid fossa is the floor of fourth ventricle. Now what about roof? Now this is important, guys. What about the roof of the fourth ventricle? Now simply we can say roof is the cerebellum only. Remove the cerebellum, then only we can see the floor part. Yes, directly you can say cerebellum, but what part of cerebellum? Or is there any special extension that we have covering the roof of the fourth ventricle? And that also we'll understand with this diagram. Here we got the pons. Let's say there is pons and medulla oblongata. And this is how the fourth ventricle was. That's the fourth ventricle. And here we got cerebellum. Now look at this. This is forming the roof in the upper part, this portion. And then below this angle, this is forming the lower part of the roof. This is fourth ventricle, and those are the extensions of the cerebellum which are forming the roof. This is referred as superior medullary velum. We call it superior medullary velum. Okay, what is that? Superior medullary velum, and this here is the inferior medullary velum. Guys, out of superior and the inferior medullary velum, the superior medullary velum is a misnomer. See, calling inferior medullary velum makes sense because it is behind the medulla oblongata, more or less. So that's fine. But superior medullary velum is present behind the pons, so that is not medullary. But it's a misnomer only, but we call the medullary velum. Superior medullary velum is a nervous structure. It is made up of white matter only. It is made up of white matter, so it's basically we have axons there, so it is a white matter. It's a nervous structure. But inferior medullary velum is having an extension of pia matter present, so it is a non-nervous structure. It is a non-nervous structure. Superior medullary velum is a nervous structure, and inferior medullary velum is a non-nervous structure. And what else you can appreciate that between the superior and the inferior medullary velum, you can see the fourth ventricle is extending backward toward the cerebellum, toward the core of the cerebellum, and that is called as the posterior recess of fourth ventricle. This is the posterior recess of fourth ventricle. So this is the fourth ventricle here. So when you see the roof, there is an extension of the fourth ventricle backward, and that you call as the posterior recess of the fourth ventricle. So this is about the dorsal and the ventral aspect of brainstem. With that, we're done with the how cranial nerves are coming out from the brainstem. We talked about interpeduncular fossa. We saw the perforating substances. We also talked about the dorsal aspect where we saw the rhomboid fossa, and again only one cranial nerve coming from the dorsal aspect. And other features of the what elevations we see in the floor of fourth ventricle, that is an important question, especially the facial colliculus part. So in the next section, we will be talking about some other major tracts inside the brainstem, like the trigeminal pathway and the auditory pathway, knowing about the lemniscus, so that we can talk about the syndromes of the brainstem. So guys, before we move on to the syndromes of the brainstem, first we need to have all four lemniscus in hand. We already talked about the medial and the spinal lemniscus in the tracts of the spinal cord. We need two more. One is the lateral lemniscus, which we'll discuss in the auditory pathway, and then there is a trigeminal lemniscus. We're going to talk about that in the trigeminal thalamic pathway. So let's start with this, and once we have all the four lemniscus in hand, then we can move on to the syndrome part. So let's look into the auditory pathway. Now, how this auditory pathway is going to be different from the other pathways we discussed? Well, till now, whatever tracts, ascending tracts or sensory pathway we saw, they were having usually three order neuron system. The dorsal root ganglia was forming the first order, second was in many cases decusating, reaching the thalamus, and the third order to the cortex. Auditory pathway is one which is having four order neuron system. So although when you look at the pathway, it begins from the ear and goes into the brain, so that it doesn't have to travel a distance like the tracts from the spinal cord does, but still the number of order neurons are more in case of auditory pathway. So first we're going to draw the plot for the auditory pathway, and then we'll see that where those order neurons are. Highest center for the auditory pathway will be the auditory cortex, or the primary auditory cortex, as you call it. This is auditory cortex. Where is auditory cortex located? It is in the temporal lobe. It is present in the temporal lobe. That is area number 41 and 42. And this auditory cortex is also called as the Hessel's cortex. There's another name given to this. This is also called as the Hessel's cortex. Auditory cortex is also called as the Hessel's cortex, area number 41 and 42. In the temporal lobe, we'll see exactly where it is in the temporal lobe when we'll talk about the cerebrum. Now, for whatever pathway we discussed till now, thalamus was the relay center. Whether it is pain, temperature, touch, pressure, everything was coming into thalamus and then radiating into the cortex. For auditory and visual pathway, It's not thalamus, it's the metathalamus, which is a relay center. And when you say metathalamus, we're talking about the medial geniculate body and lateral geniculate body. Now, to remember which geniculate body is for the auditory pathway and which one is for the visual pathway, a simple trick you can remember. Let's say if I write like this is the two geniculate body. You will see the two geniculate body present behind the thalamus, guys. We will discuss it later. But let's say this is thalamus. So behind the thalamus, we'll be looking at the medial geniculate body, and there will be the lateral geniculate body. Now, when you look at the medial and lateral, just think of M and L. M for medial geniculate, and M will remind you of music. L for lateral geniculate body, and L will remind you of light. Light and music. So it's quite clear that medial geniculate body is related to the auditory pathway. Music will remind you of the auditory pathway, and light will remind you of the visual pathway. Music and light. So when we'll look into the visual pathway, the optic chiasma, the optic tract will go backward, and that will have a relay in the lateral geniculate body and then into the visual cortex. Auditory pathway, after decussation, will come into medial geniculate body and then into auditory cortex. So this is the geniculate body of concern for this tract. So coming back to the pathway we're discussing, so we don't need thalamus here, we need metathalamus, and what part of metathalamus? That is the medial geniculate body. Now the question is, medial geniculate body will be receiving the fiber from which part of the brainstem? Well, midbrain. Midbrain section can be taken at the level of superior colliculus and inferior colliculus. And you should remember that superior colliculus is connected to the lateral geniculate body, and inferior colliculus is connected to medial geniculate body. So it is inferior colliculus. This is inferior colliculus of midbrain. This is inferior colliculus of midbrain, which will be seen connected to the medial geniculate body by a white matter bundle. It is connected to the medial geniculate body by a white matter bundle. This white matter bundle can be called as the inferior brachium. Now again, let me tell you something separately. Again, we said medial and lateral geniculate body. When you look at these, guys, if this was the midbrain, just drawing it very roughly, here was the two superior colliculus, two inferior colliculus. The superior colliculus and that is inferior colliculus. And somewhere above, let's say we got the geniculate bodies here. If for the convenience, if I say this is the lateral geniculate and this is the medial geniculate body, so what you see, a white matter bundle is connecting the inferior colliculus to medial geniculate, and a white matter bundle will connect the superior colliculus to lateral geniculate body, and that is to be seen on both the sides. Same story. So when auditory pathway will be coming from below like this in the brainstem to the inferior colliculus, so it can use this brachium and reach the medial geniculate body, and from there it can go into the cortex. So that's a connection. That's a connection band. These white matter bundles are the connecting link between the midbrain and metathalamus. Superior colliculus is above, so it is connected to lateral geniculate body by the brachium, which is also called a superior brachium. It is above, so we call it superior brachium. Inferior colliculus is below, so it is connected to medial geniculate body by what brachium? Inferior brachium. And that's what we just said, that this brachium here, which is connecting, if I just mark it and write it separately somewhere, connecting the inferior colliculus of midbrain to the medial geniculate body, that is the inferior brachium. Brachium, just a white matter bundle only, nothing special. It's a white matter bundle connecting the medial geniculate body and inferior colliculus. Considering this as a midline of the brainstem, this is a midline of the brainstem. So we already said inferior colliculus, so that means we are in midbrain. Let's come below the midbrain in the pons, and there is a nucleus present in the pons which has relation to the auditory pathway, and we call it superior olivary nucleus. This nucleus is called as superior olivary nucleus. The situation is in pons. Superior olivary nucleus. Remember, inferior olivary nucleus was forming olive. Olive was a part of medulla oblongata. This is superior olivary nucleus which is in pons. Inferior is in medulla, superior olivary nucleus is in pons. Another component that we require for the auditory pathway. Now see, guys, this was what midbrain. This here is pons. Let's go below. We'll go to the medulla. So we're going downward toward the medulla. At pontomedullary junction. At pontomedullary junction on the contralateral side, I'm drawing these cochlear nuclei. Obviously, we're talking about the auditory pathway, so we need cochlear nuclei. And these cochlear nuclei are situated at close to pontomedullary junction. Something we discussed in the cranial nerve nucleus column also. Vestibulocochlear, if you remember, vestibulocochlear nucleus were in the last column, SSA, special somatic afferent. And the situation of vestibulocochlear nucleus is more or less at the pontomedullary junction. Now the question is where auditory pathway will begin from. Now these are the components we're talking about, but where exactly it will start from? It will start from the internal ear. We all know in the internal ear we have organ of Corte, which is having hair cell, inner hair cell and the outer hair cell. So let's say these are the inner and the outer hair cell, just drawing it. Inner hair cells, and we also have outer hair cells situated in the organ of Corte, in the internal ear. So this is the point from where the auditory pathway will begin. But will it start mainly from the inner hair cell or outer hair cell? The first order afferent pathway of the auditory, this afferent neuron of the auditory pathway will start from which hair cell? Well, it predominantly will start from the inner hair cell. From the inner hair cells, 95% fiber will come from the inner hair cell, and only 5% fibers will come from the outer hair cell. 95% fibers will start from inner hair cell, and only 5% fiber will start from the outer hair cell. So what is that first order neuron which is predominantly starting from inner hair cell? That is the peripheral process and the central process of this neuron, which is connecting the inner hair cell to the cochlear nucleus of the same side of course. And this ganglion that I just drew, this ganglion is situated in the wall of cochlea. Its wall of cochlea, what is the shape of wall of cochlea? It's a spiral shape, and that's why it is also called as a spiral ganglion. It is present in the wall of cochlea, and that's why it is called a spiral ganglion, and this is the first order neuron for the auditory pathway. I keep highlighting these order neurons. That's a spiral ganglion, which is basically the component of 8th nerve only, is the first order neuron of auditory pathway. How spiral ganglion is different from the other first order neuron we discussed in the spinal cord? They were dorsal root ganglia. Dorsal root ganglia were pseudo-unipolar. The fiber comes in from the same pole and exits from the same pole. So that was pseudo-unipolar. This is not pseudo-unipolar, this is bipolar. You can see from both the ends. We have one is a peripheral, this is the peripheral process, and that is the central process going towards the central nervous system. So it's a bipolar neuron, ganglion, and they are the one forming the first order neuron. Cochlear nucleus is the point from where the second order neuron will begin, and as you know the property, if the decussation has to take place, it is by the second order neuron. So that is what is happening here. Second order neuron starting from the cochlear nucleus will decussate to the other side and reach the superior olivary nucleus. So these decussating second order neuron from the right to left and left to right side, they decussate in such a way that in the pons, in the middle part of the pons, they form a shape like a trapezium. And that's why it is called as trapezoid body. We call it trapezoid body. The second order neurons only. So don't get confused with the word body here. Trapezoid body are the second order neuron which starts from cochlear nucleus, crosses the midline and goes to the superior olivary nucleus of the other side. So these decussating neuron in the pons, they form a trapezium over there and we simply call it trapezoid body. From superior olivary nucleus, this third order neuron will begin, and this third order neuron will ascend upward, reach the inferior colliculus. Yes, it gives few collateral to inferior colliculus because inferior colliculus is related, having a relation to the auditory reflexes. So yes, few fibers will relate to inferior colliculus, but majority of the fibers will continue their journey through inferior brachium and end in medial geniculate body. I repeat again what I said. Third order neuron starts from superior olivary nucleus, ascend, reaches inferior colliculus. Few will relate in the inferior colliculus and have a relation for the auditory reflexes, but majority of the fibers using the inferior brachium reach the medial geniculate body. Now I hope you can think about what this should be called as. I told you once the tract reaches the opposite side and present in the brainstem, we call it lemniscus. It is again reaching the other side, and in the brainstem it is lemniscus. So this third order neuron is called as the lateral lemniscus. This is what we were waiting for. Lateral lemniscus is the third order neuron here. First order is spiral ganglion, second is trapezoid body, third order is lateral lemniscus, which is obviously on the contralateral side. I told you lemniscus are all on the contralateral side. That's why injury to lemniscus effect is always contralateral. And finally, fourth order neuron, which will begin from this medial geniculate body, will be radiating into the auditory cortex or Hassel's cortex, and that's why it is called as the auditory radiation. We call it auditory radiations. That is the fourth order neuron. That is the fourth order neuron, the auditory radiation. See, there is another name given to the auditory radiation. And what is that? Auditory radiation, I mean, this is a schematic diagram, so it looks like they are going superiorly in the temporal lobe. But no, when you compare the medial geniculate body and this auditory cortex is below. Medial geniculate body is above and auditory cortex is lower than that in actual. So the fibers, once they reach the medial geniculate body, they have to come in the downward direction to reach the temporal lobe. And that's why based on this direction, we can also call auditory radiation as inferior thalamic radiation. Inferior because they have to come down towards the temporal lobe. And why word thalamic? Because geniculate body are the part of metathalamus. So the word thalamic can be there. It's a part of it. Medial and lateral geniculate body, developmentally, or you can say from the evolutionary history point of view, they are considered as detached part of thalamus only. Medial and lateral geniculate body, they are in a way a detached part of thalamus. We call it metathalamus. So any radiation or any fibers coming out from there can also be called as thalamic radiation. And based on the direction coming downward, we can call them inferior thalamic radiation. So this auditory radiation can also be called as inferior thalamic radiation. You should know all these alternative names so that you don't get confused in the questions. Inferior thalamic radiations. And if you keep the same concept in mind, what would be the name? What would be the other name for the optic radiations or visual radiations? Now, optic radiations will come from the lateral geniculate body. And where is the visual cortex? Visual cortex is at the back, occipital lobe. So they have to go in the backward direction, in the posterior direction. And that's why optic radiation is also called as posterior thalamic radiation. Inferior thalamic radiation is another name for auditory radiation. Posterior thalamic radiation is a name for the optic radiation. Optic radiation. Well, all in all, in this auditory pathway, there are a few important things to note. That first of all, we got four order neuron system here: spiral ganglion, trapezoid body, lateral lemniscus, and auditory radiation. This is I told you the pathway. It's a very popular and common question nowadays to ask that they give you randomly any four option and will ask you to arrange this pathway in a sequence. So you should know this auditory or visual or any other ascending or descending pathway based on this component that from peripheral to central and from central to peripheral. So you cannot miss any of these components. But another question which is asked from the same topic only was about that which nucleus is the center for stapedial reflex. Center for stapedial reflex. Now for the stapedial reflex also, the afferent fiber are the same, only the spiral ganglion will carry the sensation to cochlear nucleus and via trapezoid body into superior olivary nucleus. Now if you go above the superior olivary nucleus, then you're going toward the higher center. Guys, when you think of stapedial reflex, we all know that stapedius muscle is supplied by facial nerve, and motor nucleus of facial nerve is in pons only. So it makes sense to have a center for stapedial reflex in pons so that the reflex can be fast. That's what the target is. We always want the sensei and motor nucleus close to each other so that the reflex could be fast. That's why from this superior olivary nucleus, you will see fibers projecting to the facial nucleus, which is in pons only, and then obviously the facial nerve will come out, and we know that facial nerve is going to supply the stapedius muscle. So please note that if the question says what is the center for stapedial reflex, your answer will be superior olivary nucleus, or you can say superior olivary complex, they also call it. That's the point where the afferent goes in, and that's how the efferent comes out. And again, the nucleus which receives the afferent and the nucleus which gives the efferent, they are close to each other, both are in pons. That makes sense. If you have a different part of the brainstem, the reflex will be slower. So superior olivary nucleus is in the pons, facial nucleus also in the pons, and that's why superior olivary nucleus is called as the center of stapedial reflex. Please note that superior olivary nucleus in the pons is the center for stapedial reflex. So with that, now we have three lemniscus in our hand. We have a medial lemniscus and spinal lemniscus we discussed in the spinal cord, and now the lateral lemniscus that we understood here in the auditory pathway. Trigeminal thalamic pathway. When the name says it all, this trigeminal nerve from the face will carry all the sensory information to the brainstem and then ultimately to the thalamus, and obviously going to the thalamus means they will be projecting into the cortex also. So once again, the component of this pathway will be, this is the sensory cortex here, this is sensory cortex, the primary sensory cortex, area number 3, 1 and 2. We are back to the thalamus here, this is thalamus. But see, what nucleus of thalamus? When we talk about trigeminal nerve, we talk about this region. I told you L and M, VPL, lower. VPM, mouth, it reminds you of mouth and face and all that region. So it's a VPM nucleus of thalamus this time, not VPL. this will be ventro-posterior-medial nucleus of thalamus, VPM nucleus of thalamus. The midline of the brainstem, the entire brainstem. And let's say on the contralateral side, here we got the trigeminal nuclei. Trigeminal nuclei. We got this mesencephalic nucleus, that is principal sensory, and there is a spinal nucleus of trigeminal. So this basically is the trigeminal nuclei, which is extending in the entire brainstem, in fact, beyond the brainstem also. This is the trigeminal ganglion. If you remember trigeminal ganglion, what was the location? It was situated in the Meckel's cave, in the middle cranial fossa in the Meckel's cave. That's trigeminal ganglion. From where you will see the trigeminal nerve coming out and giving the sensory innervation to the face. We're talking about only the sensory innervation here. So the trigeminal nerve, obviously, if I just use a different color here, ophthalmic nerve, where it goes in, maxillary nerve getting the sensation from this part, and then sensory part of mandibular nerve. Guys, mandibular is a mixed nerve. So just saying mandibular nerve is not enough, it's a sensory division of mandibular nerve. Ophthalmic is sensory anyways, that is ophthalmic. This is maxillary, but mandibular is mixed. So we are looking at the sensory part of mandibular nerve. Motor part has nothing to do with this ganglion, that will be coming out separately and supplying the muscle of mastication. So all these nerves, when they go inside to the trigeminal ganglion, they have the ganglion inside, and from where the central fibers will come and project into the different part of the trigeminal nuclei, depending upon what sensation they are carrying. If it is proprioception, we know that it will go into the mesencephalic nucleus. If it is touch and pressure, it will go into the principal sensory, and if it is pain and temperature, it will go into the spinal nucleus. But there is something very interesting to note here, that trigeminal ganglion, it looks almost like a dorsal root ganglia only. I mean, location is different, the size is different, that is fine. But dorsal root ganglia, when we talk about the spinothalamic or dorsal column tract, dorsal root ganglia was the first order neuron. This trigeminal ganglion is also first order neuron. Dorsal root ganglia was pseudo-unipolar. Fiber comes in, and from the same pole they goes out toward the central part. Same story here. Fiber comes in, goes to this nucleus, and from the same end they go toward the central part. So they're not relaying here. So it's again pseudo-unipolar. So function-wise or histologically, you can say that trigeminal ganglion and dorsal root ganglia, they're more or less the same only. Location, size, all that is different, of course. So guys, whatever I drew in red here, this whole thing is the first order neuron. This is the first order. Everything in here is the first order neuron from here till nucleus. Now nucleus is the point where they relay. Nucleus is the point where they relay. So from the nuclei, the second order neuron will begin. And you know the property of second order neuron, they will decussate. So they, let's say, just a rough diagram only. So they decussate to the other side, these are all second order neuron. And once they decussate to the other side, they all join together and relay in thalamus by forming a lemniscus. Now this lemniscus here is called as the, it's simple, it's trigeminal pathway. The lemniscus is also called as a trigeminal lemniscus. And of course this is going to be the second order neuron. First order neuron was the trigeminal nerve, ganglion, till the nuclei, everything is first order neuron. From nuclei, the one which decussate to the other side and reach the thalamus, VPM nucleus of thalamus, that lemniscus is trigeminal lemniscus. And rest of the story same, the third order neuron from the thalamus is going to project in the sensory cortex. Thalamic radiations, the third order neuron. First order, second order, and third order. So guys, with that, we got all the four lemniscus now. Medial and you should know that where the lemniscus, we expect to see these lemniscus and where not. In the transverse section of the brainstem, I've seen people usually try to mug up that what nuclei or what lemniscus is where. These are simple basics, or if you understand that the meaning of lemniscus, which tract it is forming, then it's not that hard to understand that lemniscus will be seen at that particular level or not. So if you talk about spinal cord, and the spinal cord, the tract of the spinal cord like dorsal column tract and spinothalamic tract are the one which are going into the brainstem and forming the spinal and medial lemniscus. But the two tracts which have to do with the head and neck part only, the trigeminal nerve and auditory pathway, they are forming the lemniscus in the brainstem, that is trigeminal and lateral lemniscus. So let's do one thing, let's summarize all the lemniscus at one place, and then we can talk about the different syndromes of the brainstem. If this here is a section of the brainstem, and just a very rough section, guys, let's say there is a midline, and we've got four lemniscus here, 1, 2, 3, 4. So we've taken a section from such a level where all four lemniscus can be seen. If we try to put up the location, obviously the one which is very much toward the medial side here, that obviously is the medial lemniscus. The one toward the lateral side is the lateral lemniscus, well the name says it all. What about remaining two? What are the remaining two? Now, the tract called as lateral spinothalamic tract. What was the tract carrying? Pain and temperature. Lateral spinothalamic tract was carrying pain and temperature. And the name says lateral spinothalamic tract. So out of the two, the lateral one is this. And which lemniscus was formed by the lateral spinothalamic tract? That was spinal lemniscus. That was spinal lemniscus. Because it is formed by the lateral spinothalamic tract, so it is more laterally placed. And then finally the only one left is the trigeminal. So that way you can remember the sequence also. Medial, lateral, obviously. Out of the spinal and trigeminal, think of spinal lemniscus as by which tract? Lateral spinothalamic tract. Place it toward the lateral side. Now guys, if there are injuries to these lemniscus, what will be the effect? So that we can write it down here and we don't have to think about it while discussing the syndromes. If there is injury to the lateral lemniscus, what will happen? Lateral lemniscus we just discussed, it is about the auditory pathway. So there will be a hearing loss. And one thing which I should write in the beginning only, that doesn't matter whichever lemniscus is injured, but one thing is common, that there has to be effect on what side? Contralateral, contralateral, contralateral. Everything is contralateral. Lemniscus are always found on the opposite side. So if injury to any lemniscus, effect has to be contralateral. Lateral lemniscus injury will lead to contralateral loss of what? Or contralateral hearing loss. Contralateral hearing loss will be there. Spinal lemniscus, what pathway? Lateral spinothalamic tract carrying pain and temperature, but carrying pain and temperature from everywhere else except the face. Face is all about trigeminal nerve and lemniscus. So spinal lemniscus injury will lead to contralateral loss of
यार बस थोड़ी देर रुक जाओ।
Pain and temperature, and when I say pain and temperature, it's pain and temperature from the body. I mean, when I say the word body, not including face in it, rest of the body. Pain and temperature from the body except face. Because for the face, we have trigeminal lemniscus. Now, of course, trigeminal lemniscus injury will lead to contralateral loss of every sensation from face. Pain, temperature, touch, pressure, proprioception, whatever is there will be gone. But just, it will be easy for us to compare the syndrome. Let us only take pain and temperature case. I repeat again, trigeminal lemniscus injury can lead to loss of all the sensation from face. But just so that we can compare the syndromes, to compare the spinal trigeminal lemniscus, I'm only looking at pain and temperature. Contralateral loss of, if I say pain and temperature, the difference this time is, it is from where? From the face. From the face. And finally, medial lemniscus injury. Medial lemniscus was formed by what? Now, there are two things in medial lemniscus. One was the dorsal column tract, and also anterior spinal thalamic tract joining it. So there will be contralateral loss of conscious proprioception, fine and crude touch, pressure, vibration, and also stereognosis. Contralateral loss of hearing loss. In lateral lemniscus, spinal lemniscus, contralateral loss of pain and temperature, in this case from the body, and in trigeminal from the face. Other sensation of face will be lost, I've not written here. And medial lemniscus, instead of writing all this, just remember dorsal column tract and anterior spinal thalamic tract will be gone. So there will be contralateral loss of conscious proprioception, touch, whether it is fine or crude, both will be gone, pressure will be gone, vibration and stereognosis will also be lost. So in syndrome, I cannot be writing write all these features over and over again. So in this case, I'll only write the contralateral loss of conscious proprioception. So every time I write conscious proprioception, what should come to your mind? Then obviously it is the dorsal column tract or medial lemniscus is gone. Now guys, just by heart these four lemniscus before we talk about the syndrome, because everything is dependent on these lemniscus only, which will be affected, which is not affected, and that's how you're going to differentiate.